Hi, it's Gadget UK here again. I thought I should do a follow-on video to that the video I did recently, Noobs Guide to Digital, because there were so many mistakes in there. Some of them were pretty fundamental, really. They were just things I wanted to just mention and talk about in a bit more detail. So in a minute we'll have a look at the cards, the NES card ROM in Hex Editor, just so that you can see the relationship there to the code that we looked at in the emulator versus the actual ROM image, because that was something we just didn't do, and I didn't really talk about the ROM image file, etc. Also control pins, you know, when I talked about the different buses there, you know, the address bus and the data bus, that's fine. You know, you do need the address bus to specify which slot, you know, which byte in memory there you want to read or write from, etc., or read or write to. But you also need some way of controlling, you know, components within the system. You know, like for example, on the cart itself, there'll be, you know, an output enable and a chip select, etc. So those, you know, I just skirted over that. But in general, you know, if you want to address a specific chip, generally there'll be some way there of actually enabling a particular chip at a given time, so that, you know, its address bus and its data bus spring to life, if you like, and available to, you know, it's available to address. So earlier in that video, when I talked about the logic, I mentioned truth tables, and I think there was a logic gate missed off there, so I'll just briefly show that. Yeah, so there's a basic example of what was meant by a truth table in that video. There's your NAND gate there, you know, so you've got the inverted output, you know, and you can see input A, input B, and you just have a column for A, a column for B in your outputs, and you just have each combination, each possible combination there with its output. So that's the truth table. So the other thing worth mentioning is the 6502, and in particular the 6502 on the NES there, the Famicom. It's probably, I think, or possibly a CMOS part. You know, it's not TTL. So it was just worth mentioning. Like I say, in general, the principles are the same. It's just all about, you know, the voltage thresholds there and the speed of these devices. But also, the other thing I didn't mention is CMOS is much more sensitive to static, you know, ESD discharge and stuff. So, you know, whereas TTL is a little bit more hardy in that sense. And in the bit of the video there where it was doing a read from 2002, that wasn't waiting for a H blank, it was waiting for a V blank. So the difference is, you know, if I zoom out a little bit here, I'll see if I can show you, but, you know, the way, you know, it draws the display here, it draws a scan line from left to right here. As soon as it gets to the end, you get your horizontal, your H blank. So, you know, the line shoots across here horizontally to the next line, does the next line, and the H blank, the next line, H blank, the next line, and so you get to 240. I think it might vary actually between the US and the PAL systems, but yeah, 240 scan lines. This might be running in 60 Hz mode, I can't remember. 240 scan lines. As soon as you get to the very end of the last scan line there, you then get the V blank, which is where it jumps right up here, and that is what we were waiting for when it was doing a read of the address 2002 there in the PPU, which is this register here in terms of, you know, the visual representation. And I'm guessing that the negative value goes in there, and when it does that read into, I can't remember what it was reading, was it reading into the accumulator? I think it may have been doing. The negative flag will be set because of that negative value. It's probably like FF or something goes in there to indicate that, you know, it's got to the V blank scenario and gone back to up here, and that takes a period of time when it hits the V blank from, you know, the end of this final scan line there. There's a number of cycles. There's a window of, I don't know how many it is, it might be several hundred or 1,000 or so. There's quite a large window of cycles that the CPU's got available to itself, while the PPU sort of prepares itself ready for the next screen draw. Something else to clarify, on the point where we did the capture on the logic analyzer there, you could see the read here. You can't quite see the instruction, but that was the instruction we were looking at, and it was reading from these two bytes here, you know, address 2002, you know, they go in reverse order. And this 00 was the CPU then, after it had read these instructions, read the address in, the next thing it was doing was reading 00 from the PPU. So that was a read, not a write. And at the same time, there was something obvious that I missed as well, and Chris Bleakley, and I think someone else actually, there were two people, mentioned this, and that is the capture prior to the bit we could relate to. That was, we saw in the sequence of events there running through the emulator. The bit right at the start of the capture was the vector of the the reset. As it read those 2 bytes off the address bus there for the reset. I might just see if I can just rewind a bit to show you that. But also the reset process itself. I think Chris was pointing out that the CPU was doing something with the program counter and the stack and stuff. Although apparently the stack can't be written to at that point because the right pin is held high during reset. But it was just interesting that I'd missed out on that. I didn't think of that. I mean, the reset part I wasn't aware of, to be honest. I wasn't aware that the CPU did anything whilst it was coming out of resets, so that was news to me. It was interesting. But the part where it reads the vector, the reset vector, as you can see here, I think, if we just step back one. So there you go, you can see the reset vector there, C000. So something else worth pointing out is that the relationship between the ROM file and an emulator is going to be different to the actual ROM image, the physical binary there, the code that we were running on the emulator there, that's going to sit in a chip on a cart somewhere. Now in the NES, you've got usually, I think, a couple of chips. This is something I'd forgotten about. And it's only really when I've looked at the physical side of the NES, themselves, the actual NES and the Famicom, I've realised that actually there's a couple of chips in a lot of scenarios. So you have the program code and the character ROM. So they're used by the PPU, the graphics, would be on a PPU ROM chip. So there is a website, I can't remember what the hell the name of the website is now, but you can go off and find that. Someone hopefully might post the link down below. But there's a website you can go to and you can type in the name of the game and it'll tell you exactly what chips are used on that cart and what the mapper is. Now the mapper is just a bit of intermediate addressing, if you like, that sits somewhere on the cart there, that allows the programmer to write maybe a specific bit or a byte to a certain address to that mapper chip, if you like, and it then it changes the addressing of, say, a large ROM chip on the cart to address more than the NES is capable of handling. So we looked at the address map there, and you could see there was a limit of how much ROM space was, how much address space was available to a ROM chip, and they got around that by, let's say, somewhere within that address space in the ROM there, they've put a little chip that tweaks the upper address bits to a larger ROM chip to allow the NES to see much larger ROMs, if that makes sense. So I'm not going to go into that in too much detail, but I just thought it was worth mentioning. And in the file, the ROM image itself, you can see I've got it open in a hex editor here. Typically you'll have, with the .NES format, you'll have a header. Now you can see it there, NES. I'll see if I can zoom in a little bit just so you can see the text there a bit better. You can see NES. So that first line of bytes there, the first 16 bytes, I believe is the header. Now you can sometimes have an optional trainer, not a trailer, a trainer, where someone's put and this would be on not on the no intro ROM set typically, is just the dump of the ROMs combined into one file. So this NES file here you're looking at, it's got the header to identify it as a NES type. You'll probably have some identifying bytes somewhere in there to identify what kind of mapper it is. It might be those ones there. And you'll have some bytes to say whether there's mirroring enabled or horizontal vertical mirroring on the PPU, but then you've got the code. This is the prog-ROM, and you can tell that because if you cast your mind back to the previous video, we saw D8 as an opcode that was disabling interrupts, was it? Or put it in decimal mode. I think that was decimal mode. Then we had 78, that was disabling interrupts, and then we had AD 2002, so you can see that there. So that was checking the PPU for the V blank, not the H blank. Yeah, so that 10 was the branch, and it was branched by that amount. And the thing I didn't explain is that's a negative value, FB. So it jumped backwards by however many bytes it was. I can't work that out. Was it about 4 bytes or something like that? 2 or 3 bytes. It wasn't very many. I think. You've got a positive 127, negative 127 in terms of values you can have there. That's jumped backwards by so many bytes. And then if we scroll through this ROM to the to the end of the program ROM, somewhere in there will be the start of the character ROM, which is referenced by the PPU. It's addressed by the PPU there for sprites and things. So finally here, a little bit more about bits and bytes and things. I didn't really explain why we use hexadecimal, and I guess this should be obvious just looking at this example here. If you consider 8 bits there of all as ones, we've got the value FF. That's much easier to represent in terms of code. You know, if you're looking at something, you know, and you will. It's one of these things. Once you get used to the bit patterns there, it's obvious what FF is. You'll always remember. You know, there's certain values, like you can remember what 80 is, what FF is, and 40. You know, certain bits being set there. But it's easier to represent that as just 2 digits in code. You know, can you imagine a load of code where you're referring to every time you write to an address or you write a byte, write a value, you put in the whole binary there in zeros and ones. That's, you know, it could get quite confusing and stuff. It's much easier to deal with hexadecimal values to represent those binary values, and it should be more evidence there if you look at, say, a 16-bit example. You know, can you imagine writing some code and writing a particular instruction? You know, put an instruction there to, you know, read something from that address into the accumulator. Well, yeah, it's really difficult dealing with all those zeros and ones like that, whereas you can just represent it with, you know, 2 8 bits, if you like, hexadecimal values there. So, you know, obviously your bits, and this is perhaps something I skirted over, you know, a bit is either 0 or 1, and then a byte obviously is 1, 2, 3, 4, 5, 6, 7, 8, 16 obviously is 2 bytes, so we've got 1, that's 8, 1, 2, 3, 4, 5, 6, 7, 8, that's 2 bytes, and 2 bytes is actually equal to a word, if I can type right, a word, 116-bit word. You can get, you know, 32-bit words. Some people refer to a 32-bit as a D word, and then obviously it's not an F word. Yeah, that's swearing. And then you've got 64 bits as well. You know, it goes on and on and on. But yeah, byte, a word. And then a nibble is something I didn't mention. It's not really relevant in this case, but some older systems dealt with nibbles, which is half a byte. Another thing worth just mentioning there, a correction. The point where I was referring to the memory map, I think I was talking about some of the address ranges there, and I mentioned, I think, FFFFF or something. I added like extra Fs and things. So just, you know, just bear in mind, sometimes with my health as it is, I add the extra F in there, if that makes sense, when I was reading through some of those. Anyway, hopefully you found that interesting. Thanks for watching. I'll see you soon.